Right, so you guys got this table in front of you. Everybody's got this table, right? Table. You guys write your name here. Write your name. All right, it's period right here. Okay. So this table has 12 examples in it. So I see 1, 2, 3, 4 examples on the front, and 4 examples here, 4 examples here. There's 12 different. Okay, 12 different examples. Right. All right. So you can solve all these with this process of conservation of energy. All right, and I'll show you guys how. So I have some questions going across the columns here. What is in the closed system? Now, if it's a closed system, that means that there's no external forces, right? Okay. There are a couple of exceptions here. There are 2 open systems. I'll talk about those later, right? But the other 10 of these are all closed systems, right? So you need to include all the objects so that there is no external force. Okay. What's the energy at point A? What's the energy at point B? Some of these might be one form of energy. Some of these might be a mix of energies. But I'll tell you where they all come from. They all come from something on this page right here. I'm going to leave this poster up for the last 20 minutes of class, and you can just like look up here and grab building blocks. This is your equation bank for today, for this packet. Right? Right. In fact, almost all of these are just the gold boxes. If you just focus on the gold boxes, right, that's not even many boxes. Right? So what do we got next? And if energy is conserved, can you say this energy is equal to this energy? Right? And then you can solve for stuff. Now, there's all kinds of questions you can ask. I have a universal question here, which is, what is the speed at point B? That might not be the optimal question for all these, but the question I'm asking, so I guess you can do that. So let's do some examples. I'm going to do some with you guys, then let you guys work independently or with each other, and I can go around and answer questions. First question, Galileo drops a ball from the leaning tower. Hey, that one's in your notes from yesterday. Galileo dropped a ball from the tower. So say, what is in the closed system? Well, we're focused on the ball, so you think the ball's in the system? Yeah, so write the ball. Right. Because if I only wrote the ball, does the ball have a force acting on it that's making it move? Yeah, and that's a what kind of force? Gravity force. And what object is providing that gravity force? The entire Earth. The entire Earth, right? The Earth's pulling the ball. So if I want it to be a closed system, I also have to include the Earth. Yeah. So I'll call this the ball Earth system. The ball Earth system. Okay. Kind of like here, if you're trying to figure out what's in the system, this poster is hanging up in our room. It tells you in the title, right? Like the block, the spring, and the Earth because it's changing height, right? I didn't include the track because the normal force is not actually doing any work on it. There's no friction, right? But okay, so back to Galileo. It's got the ball Earth system. Okay, you guys got the ball Earth system. Right? Guys, what type of energy at point A? Potential energy, gravitational potential. And the formula for that goes mgh. And you know that because it's right here. Right? I mean, these are all really short formulas. I bet it's not going to take too long to kind of memorize these anyway. Right? mgh. Right? What type of energy? Let's say right before it hits the ground, it's moving really fast. It has all what type energy? Call it kinetic. That's 1/2 mv squared. Right? Throw some subscripts. Subscript A here, subscript B here. Right? Right? Guys, is this energy equal to this energy? Same energy? I say just say equals, right? Just like in your notes from yesterday. Okay. Now you can solve for stuff. So let's say, well, here, I have the question right here. Solve for speed at point B. So let's solve for this speed right here. Solve for the speed right here. So I'll do the whole process here, which is what you have in your notes from yesterday anyway. Sum of energy at point A equals sum of energy at point B. Well, the energy at point A, there's only one type of energy, mgh. Energy at point B, well, there's, again, only one type, but now it's 1/2 mv squared. The m cancels out, like has every time we've done the story, just in different contexts. Solve for v times 2, square root. The speed at point B is, drum roll, square root 2gh. Just like it was yesterday, just like it was back in September when we solved that with kinematic. That's it, square root 2gh. That's the answer to the first one. That's it. That's the whole thing. Right? You guys good? Right. So here, recap how to think of these. The objects in the system are whatever creates a closed system so that there's no external force. What types of energy do you have at any point? It might be more than one type for some of these scenarios. Probably is. Right? Just pull up this page, especially focus on these gold boxes. If you see a spring, I see a spring there. I see a spring there. I see a spring there. Some of these are springs. Guys, if you see a spring, what is spring energy? 1/2 kx squared. I bet that's going to be involved one way or another. Right. Now, I told you guys there's only 2 examples in this whole packet that are open systems, and they're both on the front. They're both right here. You guys see open system, open system. These are a little bit different than the other ones. So I want to do one of these with you guys. Let's do the car braking to a stop. You guys see car braking to a stop at the very bottom. So let's focus on the car. You guys write the car. Right. Now, I'm not going to include the earth because the car is not going up any hills and it's not going into any valleys. It's not changing its height. Okay. Now, guys, as the car is braking to a stop, what object is providing the force? Yeah, the friction from the road, right? Now, here's where this is going to be a little different than most of these. I'm not going to include the road. I'm just going to only focus on the car. Since there is an external force that's provided from the road, then what that means is it's an open system, right? Just like it says, right? Which means that these boxes are a little different. Guys, for these two, for the two open systems, do this. Put a big old bubble right here in the middle. Put a big old bubble. So same thing for this one. Got a big old bubble right here. About size of a $50. Big old bubble. You guys got a couple of big old bubbles? Right. This is only for the open systems. Again, there's only 2 open systems on this whole packet. Okay. The rest of them are closed, like Galileo up here. Okay. All right. So let's hunt around. Because when the car was in motion, what type of energy did it have? Kinetic, 1/2 mv squared. Okay. When the car came to a complete stop, now it's not moving. Does it have kinetic energy anymore? No. Did it go up any hills? Does it have any potential energy? No. Did it run into any springs? No. Where'd all the energy go? Or how much energy does it have? 0 joules. Right. Now, and where'd that energy go? And a work done by friction, right? Didn't work done by friction subtract off energy from the car? Mechanical energy? Right. So, guys, in this bubble right here, we're going to complete the equation. It goes like this. Minus, what's the formula for work? Force times distance. So can I say friction force times stopping distance? Well, I have it labeled X here, so you can do X, you can do D. Just pick your favorite, either X or D. Okay. Okay. And say equals 0 joules. That's the full equation. 1/2 mv squared that it started with, minus friction force times stopping distance, ends up with 0 joules energy for the car. Okay. Okay. Now, guys, did that energy disappear from the universe? No. Right. Suppose you put a thermometer on the road and you measure the temperature before the car came across. It's like, okay, it's so many degrees. Right? And the car breaks to a stop and you measure the temperature after. Do you think that road warms up a little bit? It sure does. And if you calculated the thermal energy, I bet it would be equal to the original 1/2 mv squared of the car. I bet it would be. Right? Right? All right. So who can tell me what is the final speed of the car? Yeah, 0 meters per second. Right. So this is probably not the best question for that scenario because it's obviously going to be 0. Right. But you don't even need equations for that. But hey, what do you guys think? Suppose you open up a physics textbook and you open up to the energy chapter and you see this scenario, car brakes to a stop. What question do you think the textbook actually would ask you? Okay, they could ask that, right? They could go one of 2 ways. If you think they're going to ask initial speed, you would have to know the braking distance, which might be, here, I'll tell you where you might see that. Suppose you're a forensic investigator one day and there's some crazy car crash and they send you out to investigate. And you look at the skid marks on the road and say, those skid marks are like 18 meters long. Well, that must have been the braking distance of the car. Hey, I can calculate how fast the car was going. You could do that, right? Right. And the other way you can do it is exactly reverse. What if you know how fast the car is going? You think you could calculate that braking distance? Right? And that's what I have a poster for. You guys see car brakes to a stop. Now, you guys have seen a poster with this exact title in the past, except it had an orange banner. And it was a car brakes to a stop. But we were interested in what's the rate the car slows to a stop, like acceleration value or deceleration maybe. Right? But now I have a new question. And that's going to be, what's the braking distance given the initial speed of the car? So here's how we do this. There's the setup. Oh, there's a general open system, right? Energy minus work equals final energy. Okay. I got 1/2 mv squared minus work done by friction is force times distance, gives you 0 joules. Okay, you guys get so far? Right. Now, I need to do a substitution here. You guys see that friction force? You guys see friction force? let's look at, ooh, look, here's a free body diagram. You guys remember a free body diagram for a car braking to a stop? You guys have seen this many times before in this class. Weight, normal force, friction force. I need an equation to relate these two vectors. Who remembers? Guys, friction force is equal to what times normal force? Coefficient of friction? FFR equals mu times Fn. You guys remember that? Right. Furthermore, this normal force is exactly equal to what? The weight. Isn't the normal force equal to the weight? Right? I did a double substitution right here. Guys, does this line look exactly like this line, except for I substituted out the friction force with this expression? Right. I did a double substitution just to save a little space because I was trying to bloat the font as big as I could. Got coefficient of friction times normal force, but instead of normal force, I just did mg for the weight. Okay, a little double substitution. Great. Now, you could go ahead and solve for, well, whatever you want. If you know d because you look at the skid marks, you could solve for v naught. Or if you know v naught, you could solve for d, which is what I did on this poster. D equals, and I got an expression. Here's the answer. Guys, this is always the answer to this very classic physics question. This is the answer. Okay? To get to the answer, which variable just canceled out? Which one's no longer there? The mass of the car. What does that mean? That means if you have a small car next to a heavy car, suppose you got your car and it's empty in one case and it's full of groceries in the next case, and they're going the same speed, make brake to a stop. Guys, which car requires a longer braking distance? The empty car or the car full of groceries? They're the same, because the mass canceled out. In fact, the relationship between speed and distance, let's focus on that. I pulled that over here. There's proportion, right? You can see proportion. I'm just focusing on these two variables. This is a really classic physics question right here. Suppose you have 3 times the speed. Guys, 3 times the speed is going to require how many times the braking distance? 9 times. Do you guys see 9 times? There. Because if you throw a factor of 3 on that V naught, the factor of 3 squared is like 9 times the braking distance. I pulled that out over here. Right? I bet some of you guys see that, but maybe not everybody. So let's do a numerical example. You guys ready? All right. So here, I'll start with the answer, which is braking distance is initial speed squared divided by Q times the coefficient of friction times the gravity field of the planet. Okay, so that's the setup. Right. And let's try this out for 2 cars. So here's what, guys, here's why I'm doing this. I've asked you guys many proportion questions over the semester, and some of you guys I think are catching on to this point. Like, okay, if I throw some coefficient on this variable, I see it's going to be squared, and it's going to show up in that variable as a squared version, right? But if you're not catching on, you can always just make up whatever numbers you want, which is exactly what I'm about to do. Suppose I have a little toy car that's going 1 meter per second, 1 meter per second, squared, divided by 2 times. Suppose I have a coefficient of friction that's like 0.5. Right, that is a fraction, 1/2. Suppose I'm on a little tiny planet with a gravity field of 1 meter per second squared. You guys get that? I'm just making up whatever numbers I want. What is the braking distance of that car right there? 1 meter. You guys see that has to come out to 1 meter? Right. I mean, it works in general for variables. It should work for any numbers I throw in. I just made up some random numbers. Right. Right. Now I'm going to go back and do the same thing, except I'm going to change one thing. I'm going to change the initial speed of the car to 3 times as fast. That'd be 3 meters per second. Throw it in the same expression. I got the same coefficient of friction. You got the same gravity field on some little tiny planet somewhere in that big old universe. Right? Guys, what is the braking distance of this car here? 9 meters. 9 meters. Right? So I think some of you guys saw this before, but if you didn't, I bet you see it now. Do you guys see that if you triple the speed and leave everything else the same, it's going to correspond to 9 times the distance, right? That's a little trick you can do. If I ever ask you a proportion question and you don't know the answer, just make up some numbers and play it out, okay? All right, so here, I wanted to do that one with you guys because I've been doing that one all day. So there's many other energy posters I want to do with you guys, but I'm going to save those for a different day. There's one more thing I want to tell you guys about this packet, which is there's a couple of challenge questions right at the end. You guys see the very last 2 scenarios. I got a ball rolling down a hill, and I got a couple of asteroids gravitationally attracting. So the ball rolling down a hill, there's energy associated with rolling, and that's this one right here. Rotational kinetic is 1/2 I omega squared. I have not even taught you guys what I means yet. It's called rotational inertia. I'll teach you guys that in like January probably. So that's a little bit of a challenge question, but see if you can make the equation. You might be able to make the equation. Okay. Then the asteroids. Guys, as these asteroids in deep space are pulling together, do you think the gravity field between them is getting stronger and stronger? Yeah. And what that means is that you cannot use MGH for our potential energy because this lowercase g is always changing. Guess what form of potential energy you actually have to use? This green one right here, negative g of m on r, which there's a lot more I want to tell you guys about this one that I'm going to say for a different day. But a little challenge question. See if you guys can get this with the asteroids. Maybe stretch your imagination a little bit. All right. So, oh, good. We got plenty of class time. Give you guys the rest of class to work on this packet. You guys do as much of the packet as you can. And in the near future, possibly tomorrow, I want to go over the answers with you guys. And you can see if you're figuring these out. All right, so I'll leave that right there for you guys. And go ahead. I'll walk around the room and answer any questions you have.